Somewhere, inside a 2 billion parameter language model, at layer 10, a tiny detector switches on. Its job is oddly specific. It fires whenever the text the model is reading is formatted as JSON. Here is the question this whole series is about. Was that detector signal computed right there at layer 10 by the model's machinery? Or was it computed much earlier, say at layer 6, and layer 10 is just holding a copy that was passed along? Carried or manufactured? It sounds almost philosophical, but it has an exact mathematical answer. By the fourth video of this series, you will derive by hand a formula that puts a hard ceiling on how much of that signal could possibly have been carried. This one. Everything you need to read it will be built from scratch. Starting now, here are the 4 tools we need. Forget everything intimidating you've heard about transformers for a moment. Here's the one picture that matters for us. For every token of text, the model maintains a single list of numbers, a vector. In the model we'll study, Gemma 2, that list is 2,304 numbers long. This vector is called the residual stream, and you can think of it as a conveyor belt or a highway running vertically through the whole network. The layers of the transformer sit alongside this highway, and every layer does the same 2-step dance. Step 1, it reads the current vector. Step 2, it computes something. Attention looks at other tokens. The MLP does some nonlinear processing, and then it adds its result back onto the stream. It never overwrites, it only ever adds. That word, adds, is the single most important fact in this series, so let's see it with real numbers. Take a toy stream with just 2 numbers, starting at 3 and 1. Suppose layer 1 computes the correction -1 plus 2. The new stream is 2, 3. Layer 2 computes +2 plus 0, and we're at 4, 3. Each layer's contribution just piles up on top of what was already there. Because layers only add, we can unroll the whole journey. The vector at any later layer equals the vector at any earlier layer, plus the sum of everything the layers in between wrote onto the stream. We'll call that sum delta. This is an exact identity, no approximation anywhere. Keep your eye on delta. It is a deeply nonlinear, complicated object, and the entire paper is a question about it. Quick check before we move on. Pause here and unroll it yourself. If the stream at layer 2 is the vector 4, 3 from our toy example, what is delta between layer 0 and layer 2? You have everything you need. Delta is 1, 2, just the 2 corrections added together. If you got that, you already own tool number 1. Tool 2. The stream is a vector of 2,300 numbers. But the model isn't thinking in terms of individual numbers. No single slot means anything by itself. The working hypothesis of modern interpretability, called the linear representation hypothesis, says concepts correspond to directions in this space. And if a concept is a direction, then measuring how much of that concept is present is a projection. You take the dot product of the stream vector with the feature's direction. Big positive number, the feature is strongly present. Near 0. Let's make that concrete with numbers you can check in your head. Say the Python direction is 0.6, 0.8, a unit vector. Text A has stream vector 5, 5, dot product 3 plus 4, which is 7. Strongly Python. Text B sits at 4 minus 3, dot product 2.4 minus 2.4, exactly 0. Not Python at all. Same vector space, same ruler, 2 very different readings. One more piece of vocabulary, and tool 2 is yours. Reading a feature is linear. Dot products don't square anything, don't gate anything, don't pass anything through a nonlinearity. Writing new content into the stream, as the layers do, can be as nonlinear as it likes. Linear reads, nonlinear writes. Hold on to that asymmetry. The whole paper lives inside it. Tool 3. Here's an awkward question. The stream has 2,304 dimensions. How many concepts does a language model track? Syntax of 40 programming languages, thousands of named people, chemical elements, moods, formats, languages, far, far more than 2,000. How do you cram 100,000 concepts into 2,300 directions? The answer is called superposition. The model uses more directions than it has dimensions, by making them nearly, but not exactly perpendicular, and relying on the fact that almost all concepts are inactive at any given moment. Picture 3 arrows in a two-dimensional plane, each pair 120 degrees apart. None is perpendicular to the others, but if only one is active at a time, you can still read each one off almost cleanly. But superposition creates a puzzle for us, the interpreters. The useful directions are hidden. Nobody hands you the list. Enter the sparse autoencoder, the SAE. It's a small learned dictionary. Its encoder looks at a stream vector and answers which few features out of a big dictionary are active right now and how strongly. Its decoder holds the dictionary itself, one direction, one column per feature. That decoder column is the object we will care about for the rest of the series. So let's give it its name. D sub F, the direction of feature F. When we said a JSON detector fires at layer 10, precisely what we meant was the dot product between the stream at layer 10 and that feature's decoder direction is large. 2 practical notes. First, in this series, the SAEs are not something we trained. Google DeepMind released GemmaScope, a full suite of pre-trained sparse autoencoders for every layer of Gemma 2. We just opened the toolbox. Second, and this detail will turn out to matter enormously in the next video, each SAE is trained at one specific layer. The dictionary at layer 10 belongs to layer 10. There is no rule connecting its directions to the dictionary at layer 6. All 3 tools on the table. The stream carries everything and layers only add. Concepts are directions, read by dot products. And SAEs hand us at each layer the directions worth reading. Now we can state the question of the paper with real precision. A feature, F, defined by the layer 10 dictionary, fires on some token. Unrolling tool 1, the stream at layer 10 equals the stream at layer 6 plus delta, everything written in between. So the feature's reading splits into 2 pieces, the part read off the old stream and the part read off delta. If the reading is essentially predictable from the layer 6 stream in a linear way, we'll say the feature was transported. If it's created inside delta by the nonlinear machinery, it was synthesized. That distinction, transported versus synthesized, is the entire paper. Why should anyone care? 3 reasons. Safety. If a dangerous feature, say one involved in a jailbreak, is transported from early layers, you can detect it early, before it acts. Debugging. If the model states a wrong fact, transport tells you which layer to blame, where the fact entered the stream versus where it was merely carried. And economy. Linear structure is cheap to predict, cheap to monitor, and cheap to edit. Nonlinear synthesis is a black box. Your homework before the next video. Genuinely do this on paper. It's 10 minutes. And next video opens with the answers. Exercise 1. Unroll the stream across 3 layers and write exactly what delta is, keeping track of what each layer's function is applied to. Be careful, it is not applied to the original vector. Exercise 2. With the Python direction 0.6.0.8, compute the reading of the stream 7.1. And exercise 3, the interesting one. Try to invent a test. Given a big bag of recorded stream vectors from layer 6 and layer 10, How would you decide whether a feature was transported or synthesized? Write your best idea down. Next time, we'll take the 3 most natural ideas, probably including yours, and watch every single one of them fail in an instructive way. See you in video 2.